So first of all, a very warm welcome from me to everyone who joined today our digital coffee break. So essential requirement, grab your coffee. My name is Angela, as John already said, and I'm responsible for marketing here at AppWorks. For those of you who don't know AppWorks yet, we are a 100% subsidiary of Premium Aerotech and part of Airbus. We design, develop, and manufacture parts which truly exploit the possibilities and benefits of additive manufacturing. And before handing over to our speaker of today, John, some technical remarks from my side. So you can see below a Q&A session next to the chat, where you can ask questions whenever they arise during the presentation. And whenever John is finished, we will answer them. The other option asking questions is that you raise your hand, and after the presentation we can unmute yourself, and then you can also speak up if you like to. Yeah, so now it's time to grab your coffee, lean back, and listen to John, our Chief Product Officer.
So, thanks very much for joining. We're really pleased about the attendance on this, considering we advertised it quite late. But we thought it's good, you know, at the time when many of us are working from home, you can probably tell that I'm working from home, that it's nice to still connect with people, even if via Zoom, and even if we're spending all day on these tools. It's nice to talk about the sort of coffee break chat, which in my experience is often about interesting things that pique our curiosity. So some of my experience, it's not in huge technical detail, but it might be something you're not familiar with, which is around the use of additive manufacturing for hybrid joining. And I hope it spurs some interest and some questions, and maybe some follow-up discussions regarding what we can do with this technology. So without further ado, I think many of you will know that where do new ideas spring from? I mean, often they spring from adversity, and the challenge with adversity is often that the new idea or the new innovation takes longer to develop than the adversity takes to resolve itself. But that's no reason to not develop it and not to try and develop something which will be useful the next time you face adversity. So the inspiration for this technology largely came from experience in Airbus. At the time, working on the A350 program, I was part of the wing team, and we were working with carbon fiber composites in the primary structure of the wing, and on a scale that hadn't really been done before, at least within Airbus. And we had this challenge that joining things in general involved a sort of black metal approach, if you've heard that term. So composite parts, awesome, great from a weight point of view, but then joining them together with fasteners created a whole world of problems that we had to try and mitigate in some way. And it just led us all to think, is there another way? Is there a better way of doing this? And that was really the inspiration for the idea of using additive manufacturing for hybrid joining. I've highlighted just on the slide just a few of the sort of issues we face, and some of you will have experienced these before. There are probably a plethora of others that I haven't thought to put there. But of course, when you apply fasteners in composites, I mean, one of the obvious ones is you've got to drill holes. Drilling holes in composites is hard enough, and the material is very abrasive on the drilling tools. But when you're drilling also through composites and metals in the same stack, the materials behave differently when they're drilled. So the size of the hole, you have to compensate with special tools, and those tools are very expensive and they wear. And so when you've got literally tens of thousands of holes to drill, that becomes quite a significant cost driver, not apart from the fact that you've got a lot of assembly operations to deal with, all the, let's say, risk of damage and concession associated with that. And then maybe the ones that started inspiring me at the start with things like weight and drag, just the fact that you've got all these fastener heads, so parasitic drag, you've got all of these fasteners which are weight, and all the joints are doubled up. So you've got flanges which are adding additional weight. And as at the time I was responsible for the weight control on the A350 wing, that was obviously my primary focus. So that's kind of where the inspiration came from. I was lucky at the time that I was working department where they were doing some really exciting stuff with additive manufacturing. And it was very much the early days of the technology. So while we could build things like you see on the screen here, it was extremely slow at the time. And if you're familiar with additive manufacturing of metals now, and you think that's slow, go back 12 years, I think roughly to when this was, and you really understand slow. 200-watt single laser. We really had to focus on what are the things you could do with the technology where you brought value through complexity with the minimum volume of material possible. And the initial concept for this type of joint was actually that we would build these pins, these small arrowhead pins, onto a pre-existing machined bracket. So all we were using additive manufacturing for was building the pins. Really grams of material, very short time to process. But in the end, we were adding the value of enabling a whole different joining methodology. Now, for those of you who are maybe scratching your head at how do you get the pins in there, if you haven't got direct experience with composites manufacturing, the obvious thing is you have to embed these before you cure the laminate. So in general, we're working with pre-preg materials. So that means you've got fibers in layers, and those fibers are already impregnated with a resin, which is still soft. It's tacky and sticky, but it's still soft. And you're laying up the laminate and then embedding the pins in and then curing it in an autoclave generally. And that's then making it go hard and locking those pins in place. And what you create is a tough, robust mechanical joint without drilling. And that was our objective. Now, obviously, just because we managed to do something that looked kind of cool, and I hope you think it looks cool, I certainly thought it looked really cool at the time, there's no guarantee that that's going to be a more efficient load path. So we didn't know at first what would happen if we apply load to these things. How would they fail? And of course, that was a journey in itself. And you can imagine in aerospace, that's an extremely long journey because you've got to answer questions about every eventuality, lightning strike testing, what happens when it gets hit by a stone on the back face, a simulation of a stone, a ball bearing, that's imparting a certain energy. Does it delaminate? All of these things we had to go through. And I can remember the very first test we did, which is pretty normal with joints, was lap shear test. And for a lap shear test, I can remember having nightmares the night before where in my dreams, these joints were like butter soft and they just failed, with no load. Because you can imagine how much of your own heart and soul has gone into getting to that point, convincing everyone it's a good idea to spend some budget on. But fortunately for me, that wasn't the case, which was largely luck. And we ended up with something that really worked. So a little bit about the integration process. Push these things into the laminate. But what we found quite quickly was that it's also important to have some kind of tooling. From one point of view, you need to be able to fixture the part if you need to maintain tight tolerances. Once that part is in that laminate, assuming you've got more than one of these parts, their relative positions need to be maintained. So you are talking about having tooling, fixturing in cases where you need to maintain a relative tolerance between parts. And locally, you need a tool called a cool tool, which is there and quite commonly used in composites anyway to maintain a tolerance. In this case, the cool tool is integrating the bracket fitting, so you're slotting it into that tool. And that's helping to maintain the profile of the laminate as you go away from the interface. Otherwise, there's, as we discovered in the early days, you can get a wrinkle in the laminate. And of course, that's defeating the object to some extent, because one of the big advantages of the joint is getting rid of the effect of drilling out a bunch of fibers which would otherwise be carrying load. Of course, if you create a big ripple in the fibers, that's as bad as drilling a hole. So the cool tool is not just about manufacturing, it's also about the quality, achieving the quality in the laminate and not disrupting the laminate when you're inserting the pins. One of the beauties of the development is the fact that we kept it such that there was minimal impact to the composites manufacturing process. That wasn't always the case. At the start, I can well remember colleagues sitting there with steel rulers trying to thread fibers over pins, but we pretty quickly realized that was going nowhere fast. So we came up with a concept instead where we had the cool tool. We used traditional processes, so either tape laying or fiber placement. And then we could produce a panel. And then the only difference is that before bagging for cure, you're inserting the pins, you're positioning the cool plate, inserting the pins. You've got something that looks like this. In this case, this was done with a hand layer. Vacuum bagging as normal. Of course, you've got to accommodate the tool. So in this case, there's a small pleat in the bag, which you would position to try and minimize the risk of the bag bursting. You often have pleats anyway on the bag because of various other tools that are involved in the process. You're vacuum bagging, you're putting it in the autoclave or the oven, and then afterwards, you remove all this stuff after it's cured, and you've got something which is essentially a hybrid part. So it's tricky to know whether to call it a joint between a metal part and a composite part, because at the previous step it is, but by this point you really talk about a hybrid part. It's part composite, part metal, and they're linked in such a way that it's a single product in the end, without a joint as such. I'll let you read through that, but essentially the obvious things you can see for this flat or nearly flat panel to do this. When you get into corners, it's not impossible, and I don't think with the camera, I tried this earlier, I don't think you can see this very well, but this is a corner fitting where the pins are inserted. You can do things like corners. It's just more involved in terms of the tooling, and generally you have a two-step process during this early phase where you lay up and then you're forming around the pins and then bagging and curing. So it is possible, but it's more difficult. That's the main, I guess, overview of the assembly process. The next thing everyone always asks is how strong it is, and as I alluded to earlier, we didn't know at the start. Of course, we know pretty well now, and without going into lots and lots of detail, we have lots and lots of test data. Just to give you a simple comparison, if you talk about shear strength, which is essentially taking the bracket and trying to move it in the same plane as the laminate, the strength of the joint that we achieve, of course, depends upon the parameterization of the pins, so how you design the array. But 50 megapascals as an average shear strength is quite achievable. And when we talk about thicknesses of laminates in the range where this is applicable, which is ideally in the range of, say, 3 to 7 millimeters, that's quite competitive compared to a bolted joint, so a higher ultimate strength than a bolted joint, and also higher than a bonded joint in pure shear. If we talk about pure tension, so pull off, trying to basically pull it out of the laminate, it's quite substantially stronger. And the main reason is that you've got so many local areas that are really gripping deep into the laminate. And so you're generating a lot more resistance to failure than with a single fastener head, or in the case of a bonded joint, generally you just remove the first ply. If you've got a good bond, you just take the first ply, the first thin layer of carbon off the rest. So that's, of course, a big advantage. And when you combine both of these, the biggest benefits are where you get into things which normally bonded joints really struggle with, which is big peel forces. So when you have combinations of shear and bending, that's where this really comes into its own, because those pins act like little anchors, little beams that also can react bending forces into the laminate. So as I said, to my delight at the time and that of all of the colleagues working on the project, it ended up being a very strong joint. And of course, that then led to years and years of development on the project, with the view of the next composite aircraft, whenever it may come, that this technology would be applied. Now, of course, the main situation, as you can imagine, in aerospace is that these projects come few, then transfer this technology to AppWorks, was to look at where else can we apply it. Airbus is an airframer. We're focused on primary structure, very critical structures, where you don't apply new things like this first. You generally apply them first in things where there are lower barriers of certification. You need less data evidence. You may still need a robust solution, but you might not need 20 years of evidence that it works in order to prove it. And so that's one of the reasons we wanted to share this with you all, was to say, look, if you have ideas about where this could be applied to solve a problem that you face, then come and speak to us, because that's really our role, is to transfer these technologies, which have been developed in aerospace for very good reasons, to areas which could also get benefit from these technologies, but in a shorter time frame. And that's really what we hope, other than just some pure curiosity, that you get out of this presentation. So hopefully I haven't overrun too much, Angela, because you know how much I love to talk, but I think we're pretty much on time, considering when we started. So I was wondering if anyone wants to raise their hand, be brave, and ask any questions. You can go as technical as you like. So I have a few questions. Right, let's have a look. Steve, do you have an experience using overmolding stretch like lattices? Could be useful. So in fact, I mean, I would say this is a form of overmolding, essentially. So the hyperjoints themselves, the pins, are an array of essentially overmolded elements, the advantage being that you don't need to physically lay the plies over them. You push them through, and the autoclave pressure, or the resin flowing back into those spots, is what is then bringing fibers back under the heads. So that's really the main advantage. But I would say it's analogous to overmolding in that respect. Surface roughness considered. Yeah, so true that high surface roughness. So the comment here from Rielson Falk is, what's the surface roughness considered? Now, actually, we try and improve the surface roughness, and it might seem counterintuitive, considering that you would expect roughness to give you more surface area for bond adhesion. The reason we try and reduce the roughness is actually to try and improve the fatigue performance of the joint. So there's a trade-off to be had between adhesion and fatigue performance. And we've actually applied one of our other technologies, which is surfing, which is for surface finishing of additive manufactured parts, to hyperjoints, and achieve very good results in terms of getting a very smooth surface finish on the pins themselves, which can then improve the fatigue performance of these types of joints. It's to be said that if they are not finished in that way, their best application one-off load cases, so to absorb a lot of energy in a crash case, with the in-service load being lower, significantly lower than that. But when you apply those surface treatments, then you can really address the fatigue critical cases. The other point on the adhesion, I would say, is another very interesting thing about the joint is adhesion actually plays a very limited role in the performance of the joint, which is, I think, a good thing. It's very difficult to prove the chemistry of adhesion is working. And that's one of the classic challenges of bonding in where it's applied, is how do you prove that a bonded joint is as strong as your reference joints that you did during certification and so on. In this case, we actually proved with some tests where we coated the pins in free coat, which is a release agent. I'm sure other release agents are available. And basically that was to test what happened with this joint. What was the strength of this joint if we just got rid of adhesion? Effectively, free coat is like covering it in wax or something very slippery. And the strength of the joint was only, I think, it was less than 10% reduced from the strength of the joint with full adhesion, showing that the primary load transfer is mechanical. And that means if the pins are there and they're in the laminate, as long as you can prove that they're there and that the fibers are around the pins again, you can be confident of the robustness of the joint. And we developed ultrasonic testing methods, which enabled us to quite easily inspect to prove that that was the case, and even to look for damage in service at the pins themselves, whether there was any fatigue damage in the pins themselves. More questions, they're still popping in. Okay, yeah, delamination. So Martino Figoni. So possible delamination issues are the consequence of impacts on the back surface. Yes, that was tested. We did, classic impact tests, ball bearing tests with different energy levels, and inspected the parts with CT scan and tested afterwards. We found that the behavior of the joint was very similar to a plain laminate when we did exactly the same test with the same laminate but no pins in it. That the damage propagation in the laminate was very similar in magnitude. There was a degree of focalization or localization of that damage around the area where the tips of the pins are. But the good thing is the tips of the pins is not where the primary load transfer occurs. So if anything, it's a similar level of damage, but it's offset into the least sensitive position in the laminate. And I mean, if you want to follow up, I think Angela will put up an email address at the end and stuff. We can, discuss in detail those results and show people if they're interested. Ben Farmer, who was involved back in those days in everything we did, criticality of pin shape. We spent a lot of time at the start, as us aerospace people tend to do, with trying to optimize things. So we did a lot of testing with different pin shapes, different, let's say, arrays of pins. We did quite quickly narrow down to the parametric definition I showed earlier, simply because you need to do any kind of optimization a certain number of variables to optimize against. And at the very start, if you go Googling, you can find the patents. The earliest patents, we drew every conceivable shape of pin that we tried. But the reality is that it was much easier and more rational to use the parametric definition that we showed there, because every parameter was somehow linked to a load case, a failure mode, and so on. So not only was it possible to optimize with a number of parameters, but you could even isolate which parameters or which combination of parameters were really going to affect a certain load case. Ben's other comment is around whether another process such as binder jetting might be less orientation sensitive and it might be a useful enabler. You're right that some of our binder jetting might be useful in terms of less orientation sensitive. In fact, we did overcome a lot of the issues with supporting these pins. You might be surprised, Ben probably isn't surprised, you might have been around when we did this, but where we could build pins completely horizontal with very, very fine supports, which really look like threads almost, and they would build successfully. So we did overcome the orientation issues to a great degree. Binder jetting, I'd say, is relatively new technology, relatively speaking. And so we remain to see, where that goes in terms of which materials. So whether titanium alloys are applicable with those technologies, and whether the performance, particularly in fatigue, are similar. But I'm definitely keeping an eye on that, because it is an interesting one in terms of productivity and so on as well. So Dave's asking, is AppWorks looking to license or otherwise partner for the development? So we effectively, in the legal framework of Airbus, we're the licensee of the technology from Airbus. What we are enabled to do is to partner with others to develop products using the technology. So we're very open to partnerships where people have an idea of how they could apply this differently, that we can apply this in a different field. But we wouldn't look to, let's say, sub-license it further and just give someone else the job that we've already been given to do, partly because we think we're best positioned anyway from a technical point of view to take it forwards. But of course, partnerships are always useful. AppWorks, as a industrial business, let's say, is very much additive manufactured, metal additive manufactured focused. And of course, to implement this, you always need a like-minded composites manufacturing business, whether that's a partner to enable a new product. But we're definitely open-minded to that, David. Another question. Angela, you might have to just stop me whenever we get to run out of time, but there's lots of questions, which is great. Did you perform a simulation of additive manufacturing process in order to find sharp deviations? Deviations of produced, or shape deviations, sorry, there's just a type of shape deviations of produced parts. So actually, I think it's not directly related necessarily to the Hyperjoint, but the answer is yes. Simulation of additive manufacturing processes to estimate deviations of parts is something that we've done. And there are some, it's still an evolving field in terms of the precision of those processes, but they do give a very good guide. And where we have particularly challenging parts, we will use simulation in order to estimate where those issues are likely to come from, and how best to address it. How stable is the connection between the printed pins and the base parts? So that's a good question, Wolfgang. In fact, today, because the additive manufacturing technology has come a long way in terms of productivity, we're generally building the pins and the part all in one piece. The interface there is, let's say, as robust as the rest of the additive manufactured part, which is, to say, very robust in terms of defect freedom. When we were printing just pins on base parts, you're right to assume that we're very sensitive to the precision of the setup of the part in the fixture to get a very precise flatness of the first layers to ensure fusion of the pins to the part. And it was possible to achieve a good quality, but it takes quite a lot in the setup and quite a bit of precision to get that. And that's partly why we've gone towards just producing the entire parts with additive manufacturing, is actually now the technology is fast enough and the trade-off sort of lends itself that way rather than fixtures, jigs, and very precise positioning of parts in the machine. Okay, so Ben's asking fatigue performance versus bonded joints. So there's a little bit actually out in public domain on fatigue performance, I believe, but I can comment on that. So from the point of view, if you compare it to a bonded joint, the fatigue performance at the higher cycle end is very similar to a bonded joint. And the reason being that most of the load transfer at those lower loads is through the bond line itself. So what you get is an SN curve, which obviously starts, if you plotted rather than intensity factor, 1 for the yield strength or the strength of the joint down to 0. For a bonded joint and a hyperjoint, the hyperjoint looks a lot worse at the high end because of the fact that the 1 is much, much higher than the bonded joint. If you normalize the two plots, the high cycle end is very similar to the bonded joint, and the low cycle end is much, much higher than the bonded joint. But Ben, I'd always be willing to go into that with you in more detail. I know you're a composites man, so you can always help me out. In terms of the stress intensity factor in critical areas of the pin, which is another question. Off the top of my head, I can't remember, but there is a known one. So I'm sorry, I can't answer that off the top of my head. But we have done, we did quite a lot of finite element analysis. And obviously these are very small features, so strain gauging and things like that isn't feasible. At least theoretically, based upon finite element models, we know a stress intensity factor, and we get very good correlation between various methods that we use. So nonlinear FEA was used, linear FEA as well. We also even went as simple as beam spring models. And actually we could get, with obviously tuning the beam spring models to what we saw in the nonlinear FEA, we were getting quite good test correlation when we change, for example, array patterns and so on. So yeah, that is something we looked into in quite some detail.
I need to play the bad guy, John, and we go for the last question.
Okay, right, there's 4 more questions. Which one do I choose? Or
you go for 2.
Okay, so one question which is another one from Martina is, does the solution work better for UD or woven fabric prepregs? I'd say from our experience, it works fine for both. So I don't think there's a noticeable difference in working with woven prepregs or UD prepregs. And obviously it's a slight, the examples I showed were with prepregs. There's also, the other side is liquid resin infusion, RTM and so on. And it can work with that. Some of the work we did in the early days was with that, but there's a lot less test data for liquid resin infusion and RTM. And there are some, let's say, advantages to prepregs in terms of the resin viscosity and the effect it has on how the fibers come back around the pins, which reduces the prevalence of resin-rich defects, which you can see with RTM and liquid resin infusion in these things. And I'm just going to go down the list. Works in resin as well as in thermoplastic matrix. So actually, Jürgen is right to raise this. He's raised it the other way around. So most of the work we did was actually with resin, so thermoset resins. But we have also done work with thermoplastic resins, which he's probably familiar with because there was a project done with, I think it was a peak-based resin. I have to check with peak-based matrix for a demonstrator project with a drive shaft, which was quite interesting. I'm not going to stop this. I'm going to keep going.
I will.
No. Failure mode for Hyperjoint is it depends on the load direction, so and how you tailor the joint. So we have models where we can tune the failure mode, but typically in shear, it's almost always a shear failure of the pins. You have to try pretty hard to get it to fail in bearing or in another mode like a laminate failure. In tension, if you don't try very hard, the easiest failure mode to achieve is a delamination around the widest point of the heads of the pins. But you can tune it so that you go towards a pull-out failure mode, which is basically tearing fibers instead, which tends to achieve a higher strength ultimately. It's all down to tuning. Causing the pins themselves to fail in tension, you can do, but again, it's at quite an extreme end of the optimization to achieve it. Does AppWorks consider the Hyperjoint to be mature enough for fracture critical primary structure? I would say it depends what you define as a primary structure. If you talk about things which are static loaded but critical, then yes, definitely. If you talk about things which are fatigue loaded but critical, I think you always need so much more data than we have, that it's a journey to get there. So I think we're more on the side of focusing for things which are where the biggest advantages would be, which is likely to be very severe extreme case in case of a crash or some kind of extreme scenario, and an in-service case which is similar to bonding, which bonding would normally be fine for, but you really struggle either with out-of-plane loads or with a big one-off load case, which you need to protect for as well. Okay, so I managed to go through all the questions. Someone added, Ben, oh, it's all right. He's okay. Ben added a comment rather than a question, so I'll let him off. Okay, there we go.
All right.
Thank you for those questions. That was something. If you do have more questions, of course, you're welcome to contact us. Angela, I don't know if, I guess they can contact the website, they can get the email address from the website and email us, and you will...
exactly. Yeah.
So that's our website, that's our phone number, and we have our next session. Angela, maybe you could, next Thursday, I guess, right? Same time.
Exactly. Next Thursday, same time, we will go for the next digital coffee break.
Yep.
Yeah, so
keep your eyes peeled. Follow AppWorks on LinkedIn to see the advert, the next one, so you see if it tickles your fancy. Thanks everyone for your engagement. It's been, I know it's not really very real because it's only me talking, but I appreciate the questions and everything. So cheers.
Yeah, thanks John, and thanks everyone participating. It was really nice, and I'm already looking forward to seeing you next week then.
Enjoy the rest of your day, everyone. Cheers.
See you then. Bye.